Ryder Strauss is a recent graduate of CU Boulder and is a project lead for RECON, the Research and Education Collaborative Occultation Network. He uses small backyard telescopes to observe tiny objects like asteroids at the far ends of the solar system, using a technique called occultation, with each occultation only lasting a fraction of a second. How much can we learn about these faraway objects that we can't see? Turns out, quite a lot. Ryder, thanks for being with us today.
Yeah, thanks for having me.
So first off, tell us a bit about RECON and how you got involved.
So how did I get involved? It was actually a little bit of a not necessarily an accident, but close to an accident. I wasn't seeking out this particular field of research or this particular position. I didn't know John Keller. I wasn't particularly involved at the Fiske Planetarium level. I was a sophomore trying to get my foot in the door a little bit on some kind of. I needed job. I needed money, and if I was going to get a job, I wanted it to be involved in research, so I could get my foot in the door. In that area. And so I went onto the APS Research Employment Opportunities page, and there were a couple of job listings there. One of them was from Nick Schneider on the Maven project, and one of them was with John Keller on the RECON project. And I applied for them both, and Nick was super quick and super proactive, and he got in touch with me right away, and I got interviews right away, and I was not hearing anything from John for a while. So eventually after my programming class one day, I headed down from the observatory to Fiske Planetarium, and I busted into his office and knocked on his door in the middle of a meeting to introduce myself and let him know that I applied and was waiting for a response. And I think that was what kind of put me on his radar, because very shortly after that, I had an interview with him. He told me a little bit about the project. Then another interview with him where he told me a little bit more about the project, and then offered me the job. And I said, yeah, sounds awesome. So and the interesting thing is, it's funny how the universe sort of works out sometimes and puts you right where you're supposed to be. This was between the two jobs, RECON was my second choice at first. I was especially excited about the Maven position, and this had a little bit more focus on the sort of education outreach side of things, which I hadn't had a whole lot of exposure to. But after getting involved with the project, it's grown to be a really, really huge part of my life, and huge part of what made my undergrad experience, my experience at CU, so awesome, and informed what I'm interested in doing moving forward with my research, and forward into grad school at Northern Arizona University, where I'll be heading in the fall.
Well, that's a pretty neat story. That's very kind of inspiring, I feel like, especially for other undergrads who are kind of like, ooh, research is something that I would like to do, but how do you do that? And what do you do if you haven't heard back from one of your people? And that's actually how I got my job at Fiske, is I called our education manager and I was like, hi, can I talk with you about working at Fiske? And she was like, okay. And then here we are. So it's always a good idea to call back or knock on the front door and say, hey, can I introduce myself and talk? Because this means a lot to me. That's always good. Mm-hmm. Tell us about RECON, the mission, and what it is, and what you're doing with it.
So RECON is a fancy NASA acronym. It stands for the Research and Education Collaborative Occultation Network. And what it is it's essentially made up of a whole bunch of teams of volunteer citizen scientists, mostly at local high schools and middle schools and a couple of local universities, all the way up and down the sort of western side of the United States, from I guess we now have some sites in Canada and all the way down to southern Arizona. And we've supplied each of these teams with a backyard 11-inch telescope and camera equipment to sort of form a picket fence or fishing trawl across the western United States to capture what's called an occultation. And an occultation is basically when a small object passes in front of a distant star. It casts a shadow of that starlight onto the face of the Earth. And if you're within that shadow, observing the star at the time of the occultation, you'll see that star blink out. And if you have enough sites within the shadow, you can measure the timing of that blink. And if you fold the timing of that blink in with the geometry of where your site is on the Earth, you can draw a picture of that shadow that you found yourself under. And because stars are super far away, the starlight is all sort of coming in perfectly parallel. And so as it turns out, the shape of the shadow forms essentially a perfect image of the shape of the object in the plane of the sky. And so we've got this big old network of citizen scientists that all go out on predetermined nights to record plus or minus 5 or 10 minutes about the predicted nominal time of when one of these events is predicted to occur. And they'll all record the videos and see if they actually see a dip. And when you see a dip, it's super exciting because you can get these really high resolution, high precision measurements of these objects that are so small and so far away that you just can't get this kind of detail on them with more traditional observational techniques.
Sure. And this is, so we actually talked with Dr. Fran Bagenal yesterday when we recorded her interview. We were talking about RECON, and I think they used a similar technique, right? Where this is such a small object, as far as looking for astronomically significant stuff in space. And so you can set up this whole network, and then you can kind of trace out the shape of whatever object. And we were talking about how, once New Horizons passed Pluto and was kind of moving forward, scientists were curious, well, what should we expect when we get there? And then you can do basically what you just said and kind of map out what it looks like. So my understanding is that you are looking for occultations that are caused by trans-Neptunian objects, right? Or TNOs. Can you tell us a bit about TNOs and why they are important to study and understand?
Yeah. So the term trans-Neptunian object, in its sort of explicit definition, it means an object that passes across Neptune's orbit at some point in its lifetime. In our sort of RECON world, we use the term TNOs as sort of a general term for outer solar system object, even though they might not strictly match the definition of a trans-Neptunian object. But the interesting part about the interesting thing about these objects in the outer solar system is that because it's so distant and so cold and things are so sparse out there, these objects haven't had very much opportunity to sort of interact with each other. And they're far from the sun. There was a lot less sort of interplanetary dust during the formation. So it wasn't the sort of violent, chaotic, super active type of region that the inner solar system when the inner planets were forming. And because of this, these objects, many of them exist much as we expect they would have been 4 billion years ago when they first formed in the during the infant years of the solar system. Actually, you mentioned RECON, and the exciting thing about RECON is it's the only one of these objects that's had direct, super high resolution spacecraft flyby measurements of it. And you look at the surface, and it's this really smooth surface that's got this sort of lobe structure that seems to indicate that these objects, it's got this double lobe structure. And oh yeah, so looking at the sort of double lobed structure of Arakoth and how sort of gentle the seam in between those two lobes are, it seems to indicate that these are two objects that very, very gently sort of accreted onto each other. And that we expect would have occurred when the solar system was still thick with accretionary dust and gas. And at the same time, these accretionary features and the entire surface of the object is covered with these a very, very sparse coating of very old craters, which is consistent with a surface that is about 4 billion years old. So Arakoth is sort of a really, really concrete piece of evidence that these objects are really primordial. And so in studying these objects that are about as primordial and as old as they come in the solar system, we can learn about the physical properties of the makeup and structure of the solar system when it was forming. And obviously that can give us insight into it's a time capsule, and it can give us insight into our history and the history of Earth and the rest of the solar system.
And just to be clear, so first of all, just for people listening that can't really see what we're doing with our hands on the screens, this object Arakoth looks like a 2-sphere snowman. And so instead of 3 snowballs, it's just 2 that are kind of stuck together, right? That's what we're talking about when we say lobes. And you mentioned that we see all these craters on the surface, cratering that is consistent with a 4 billion year old object. And so, and we astronomers use cratering to tell us about the age of the surface of something, right? And so, because if the thing is hot, right, say this object Arakoth, then something might happen, volcanic eruption or plate tectonics, to erase those craters. And so when we see the craters on objects, then it kind of gives us an estimate as to how old. Is that right? And that's also why we think, why we know that the moon is super old and not renewing its surface, because we see all these craters on it. So just to clear that up really quick.
Yeah, that actually leads in perfectly to our next question, which is just kind of, what is the overall goal of RECON, basically? You're doing all these observations. Are you guys like making a catalog, or are these actually being used to study these objects further? What's going on there?
Yeah, so the overall goal of RECON is to study and understand the physical composition and makeup of these individual objects. Lots of other there are lots of other surveys that study the outer solar system, but many of them study it sort of more as a bulk population. They study, the overall structure of the outer solar system and the sort of dynamics of it. And we're slightly more interested in the sort of physical makeup of these objects. What are they made of? What are they shaped like? How shiny are they? How dense and massive are they? And so everything we are trying to do with RECON is trying to answer those questions, essentially.
Okay, so you're getting like into the nitty gritty rather than sort of a big picture sort of thing.
Yeah, it's a very, very object by object effort, and that's actually an interesting sort of strength and weakness of RECON. Is the outer solar system is hard to study, even by occultation. It's really hard to study because when you get these, you need to get a prediction of when an object is going to pass in front of a star. And so you need to know where the object is in the sky and what direction it's heading, so you can predict sort of what its trajectory is. And to do that, you need observations with really big telescopes. And you take these observations with these really big telescopes, and you get a sort of physical, what's called an astrometric measurement of where the object is in the sky. These feed into the predictions. These astrometric measurements are really easy to obtain for say, main belt asteroids, so asteroids in the asteroid belt and near Earth objects. Those objects are very bright and they're very easy to observe with even a smaller telescope. Trans-Neptunian objects are very hard to observe. You need a very big telescope with a lot of light collecting area because they are super duper dim. And you need to take really long exposures again, so you can collect as much light as possible. And because they're so far away, just because of the way the geometry works out, you have some given angular uncertainty in the position of the object in the sky. For an object that's closer to us, a 1 degree angular uncertainty corresponds to a much smaller distance than an object that's way far away from us. And so because of those two factors, you have these really large uncertainties on the position of the object, and therefore you have really large uncertainties on the position of where that shadow is going to fall on the face of the Earth. So because we have these really high uncertainties, we need to space, even though we've got a huge network of a bunch of telescopes, there's like 55 telescopes, we need to space them pretty far apart so we can cover a really wide uncertainty region on the surface of the Earth. And because of this, if we get a detection, these telescope sites are spaced really far apart. And so it's very rare for us to get sort of really high resolution, high spatial resolution on the profiles of these objects. Typically, we'll have 1 or 2 or 3 detections, which can give us some constraints as to, is this object obviously really non-circular, or is it probably pretty circular? Is this object really big or really small? These sort of broad measurements. The important thing with an occultation is these astrometric measurements that I was mentioning with the big telescopes. When you observe an occultation, even with just one sight, you know for sure that at that moment, the object was at exactly the same place in the sky as that star. And because of the Gaia satellite and the Gaia catalog, we know the positions of these stars to a really high uncertainty. And so that occultation detection provides an incredibly precise astrometric measurement of the position of an object. And these occultation measurements can be so precise in terms of astrometry that they can feed into other future better predictions for occultations. That's what happened with Arakoth. Is there was occultation effort after occultation effort after occultation effort. And even though this is a very distant object in the trans-Neptunian population, for that final occultation campaign where you saw that they got enough resolution on the object to see that double lobe structure, that was because they had taken these measurements so many times before that the uncertainties on that shadow had really narrowed down, and they were able to send 20 or 40 telescopes and space them really tightly, 5 kilometers apart, to really get that high resolution. So that's the other thing that the sort of goal of RECON is to provide these it's a gift that keeps on giving, a positive occultation detection, because if we can get with RECON a really broad detection, we can think about going after sort of more focused, higher precision, more targeted occultations.
Yeah, I remember when the Arakoth occultations were happening, and it was like, all right, so now we know that it's 30 meters across and shaped like a peanut. And then 2 months from now, we'll know a little bit more, and then we'll find out more and more. And then by the time we got there, it was shocking to me how accurate the occultation represented the actual object. Like when we got there and took pictures of it, it looked just like the shadow did.
Yeah, it's really cool. Amazing.
So obviously occultations, you have to be out at night, probably pretty late. Unlike, somebody like me who uses spacecraft data, we can just work whenever, but you are very tied to working at specific times. Is that something that you enjoy, being out at like 3 a.m. in December, or are there some specific challenges perhaps with this nighttime observing?
Well, there are absolutely challenges, and obviously, observing at 2 a.m. in December is much less pleasant than observing at 2 a.m. in July. But I'm in love with it. I think being at a telescope, taking data yourself, looking at the universe, for me, it's sort of the purest form of astronomy, and it's really rewarding to be there with the equipment, taking the data yourself, um, and I think the difficulties and the challenges of needing to be at the telescope, and obviously you're dealing with weather. I'm super excited, I just got time on the Apache Point 3.5 meter telescope to observe this target of opportunity, and then you stay up from 1 in the morning until 6 in the morning waiting for clouds to clear or humidity to go down, and you don't end up taking data, and that can be really frustrating, and so I think it's important to obviously have a sense of humor about it. Like, we're a bunch of nerds hanging out with big telescopes, and that's like fun and cool and funny, and also I think when you do get a really good night of observing, getting that data and looking at that data that you've retrieved is sufficiently rewarding, whether it's waiting for humidity to clear at a really big telescope in Arizona or New Mexico that you're remotely observing, or on the little 11-inch RECON telescopes when you see your first occultation for the very first time. The level of sort of excitement and how rewarding it is I think pretty unmatched, as I found in my sort of academic and career, and my time as an astronomer. So yeah, it has its share of challenges, but it's absolutely worth it.
And I think that would be, kind of one of the strengths of a program like RECON. Like you were saying, you have telescopes all up and down the West Coast. So, if San Francisco is rained out, you might have somebody in Portland that actually got the occultation, or vice versa, or what have you. So it seems like having this whole network online really beefs up your chances of getting really good data.
Yeah. It can sometimes be unfortunate when it's super duper clear in southern Arizona, because of course it is, and obviously in Seattle it's rainy, and if the occultation shadow falls over Seattle, then we're out of luck. Looking through our positive detections that we've had, the vast majority of them have been detected from sort of southern Oregon, northern Nevada, southwards. And I noticed this, and I thought this was interesting. For a split second, I thought, oh, that's weird. That seems like a surprising bias. And then I realized, oh, that's because that's the part of the network that actually has clear skies. So if a shadow passes over the northern part of the network, we're less likely to actually observe it. So shout out to the observers up in Washington and in Oregon for being troopers and getting out there and observing whenever you can. I know the weather is problematic, and in the winter, I think sometimes those observers up north get frustrated with the observers down in Southern California, their wonderful 70-degree nights.
I remember being in Arizona. A big part of my family lives there, for Thanksgiving a couple of years ago. And it was obviously the end of November. And I walked outside and I was like, wow, it's hot. I want to go back inside where it's cool because there's air conditioning. And this was like in the middle of the night. And I was like, wait a second. it's almost December, and I'm going back inside to stay cool, which is very abnormal coming from Colorado because the snow. Yeah, I remember showing. I have a Meade 90 millimeter telescope, and
I think I have the same telescope.
the ETX 90.
Yep.
Yeah. Yep. Yeah, it's a great scope.
It's right in the other room.
That Maxitov Cassegrain. I remember showing my friends and some family members and some people on my street. I had it set up just right outside, and I was looking at Jupiter and Saturn, because they're right there. One summer night, this was last year, and the first time, it's like it was much more common than I would have expected for people to look through the telescope and see the rings of Saturn or the stripes of Jupiter and the Galilean moons and just cry, because it's the first time you see those objects like for real. You're literally seeing light that is coming from those objects being directed, by a mirror into your eye. And it's hard to describe kind of how powerful that is. It's very cool.
Mm-hmm.
So sorry, we're going to go ahead and kind of change gears here a little bit.
For sure.
Ryder, you and I have spent time together in some courses, actually.
Yes, we have.
Most recently, Doug Duncan's data analysis course. And so when I was, drafting up some questions for this interview, I was like, this isn't really the theme of the program, but I thought I'd ask you a little bit about some programming, because that seems to be a common interest, and it's an important thing in today's astronomy world. So, obviously today's astronomers, and like most scientists and people in general, are using computers to do lots of things. So from what you've seen and worked on from your vantage point, if you had to kind of sum it up yourself, what role do computers play in astronomical research?
I don't want to say they're everything, because that's not strictly true, but sometimes it feels like they're everything. In the last century, maybe it made sense to do real cutting edge astronomical work by hand, timing things. When people first started doing occultations, they looked through the eyepiece and they had a stopwatch, and they clicked it when the star went off and clicked it when the star went on. But as we learn more and more, I think it gets harder and harder to learn new things without the use of technology, which is why it's awesome that technology has come so far and is such an amazing tool. But we use computers in almost every single step of our pipeline, from our astrometry and our predictions of, computers are doing the calculations of, is this object going to pass in front of the star? Where is the shadow going to fall on the Earth? What is the probability that if the whole network observes, we'll see the occultation? And then the telescopes themselves are computer controlled, and they gotta track the motion of the stars in the sky. And then when we get the data, we're using computers and we're using code to find the stars and find the star that's supposed to be blinking out, and go through every frame of the video and measure how bright that star is and look for a dip in the brightness of that star. And then we use another computer to take all of those light curves from all of those different sites and combine them together into a single plot that's plotted in the plane of the sky, so we can see what shape the object makes in the sky. And then we use another computer to take in that sort of time corrected sky plane corrected light curve data, and run simulations to determine what is the most probable size and shape and position of the center of the object. So computers are and code and programming is crucial in every single step of our pipeline, from start to finish of the analysis. Yeah.
Well, it makes sense that more and more, schools are starting to require that their astronomy majors take some computer science courses, because it almost seems like even if have all the stuff, all the physics and the math and the astronomy, once you get to a research level, if you don't have the computer skills, then you can't really put your knowledge to work because you need the computers to do that, kind of quick math for you.
Absolutely, absolutely. And a little tiny jab at CU here. They don't require, or at least for my degree, they did not require any programming or computers of any sort whatsoever to graduate in astrophysics. And
it's just a strong suggestion.
It's a strong suggestion, and it's something that, to their credit, they've done a very good job of saying, sort of in the mentoring meetings. And if you want to do research, you have to learn to code. You have to take Astro 2600, the intro programming class. But it seems to me like a fallacy that it is not a required class for the major, because I found both in my upper division classes, if I had not taken a coding class and learned to code, I use Python so much in my upper division classes, and especially in my work with RECON all the way. I'm reading other people's code and using other people's code, and also, oh, you don't have a tool for that? Well, here, let me make a tool for that. And having the ability to write a tool that you need is so crucial and so useful.
And, with RECON specifically and these occultations, some of these occultations last fractions of a second. So I imagine that stopwatch method is not very effective or accurate at all when it comes down to these, half-second observations. You've really got to get good precision, and you can't do that by hand.
Right. And not only do they last very short, but we're also dealing with really dim stars. So we're taking really long exposures with our camera, and your eyes cannot expose as long as a really good CCD camera can. And your eyes can't measure, you can measure, oh, that's when I see the star blink out, and that's when I see the star come back. And that's really easy to do with a bright star and a big object. But we have dim stars and small objects. And sometimes it's a specific example, but if we have an occultation by an object that's really small, it can occult the star for, say, half a second. And if we're doing, 1 second or 2 second exposures just to get enough signal to noise on the star, that occultation isn't going to show up in the video as the star blinked out. The star will be visible because for most of that exposure, the star will have been visible. And so part of what our software does is it looks at, okay, what fraction of this integration was the star blinked out? What percentage of the sort of total starlight is actually visible at this time? And so the kind of precision that we need to work at here to be able to tease real useful data out of this really messy and not super clean and easy to observe systems and phenomena. You can't do it by hand.
Listen, Tara, I don't know how good your stopwatch thumb is, but I've spent years developing my stopwatch clicking time. So it is instant and precise now.
I am not that accurate.
Ryder, what's the biggest challenge that you have faced when writing a program for your astronomy-related work? Have you ever run into something especially frustrating? And, how did you work around that? And if you haven't, that's okay too. If you've just always been a wizard and you're like, done, then that's, that's how that is.
No. I think my biggest challenge, and it comes, I think, to a flaw in my own programming, is I don't comment things for myself. I just sort of code and go. And I'll write sometimes more lines of code than I probably wished I would have before I try running it, and realize that it's broken. And so the biggest sort of most important lesson in error handling and debugging and dealing with problems in your code that I was taught by Seth Hornstein, bless his heart, when he was first teaching me Python, was print statements everywhere. If there's an output that you can print, if it immediately gets fed into another function or another variable before it gets fed into that new function or new variable, print it out and make sure that it's outputting what you want it to output, without being able to provide any specific examples of especially sort of challenging coding issues I've had. That's sort of the overarching fix, is print statements everywhere can do more to fix your code and help you find the problem than any fancy cool IDE with a debugger. And sometimes even you'll write syntax that you'll think is right and it just won't be right, and it's not immediately clear to the eye. And so there have been times, and it's been a bummer, but there have been times when I've just had to scrap a program and rewrite it from scratch. I had a final project for my planets, moons, and rings class. So we were simulating cratering on a surface, and trying to figure out how long it would take of craters hitting the surface before the surface reached saturation. Essentially, it's as cratered as it's ever going to be. And my system was never ever saturating, and so I started my loop and it would just run forever and ever and ever. And I compared with friends who had written the same code and theirs was working, and I combed through line by line and I filled it with print statements, and I just could not find what was wrong. So I deleted it. I didn't actually delete it, but I moved into a new cell, and I started writing the exact same program from scratch, not having changed anything about my logic or what I thought the syntax was doing. There was some dumb error in there that was causing it to break, that on my second type through did not exist, and the program was working as I wanted it to. It's important to have patience with yourself and patience with the software. Yeah.
Those little bugs are all too common. Just this morning, I was talking with my teacher for one of my classes about a program that I had written, and we were looking, and there's supposed to be this output that wasn't showing up, and we spent like 5 minutes trying to figure out, why is this not showing up? It very clearly should. And I didn't enter a new line return on the output, so it was the output and then the next console statement piece there. So it was totally blending in. We were like, it should be there, but it's not there, and it was. And we're just dumb.
I think that's a universal experience. I've had that same thing where you write a whole big line and it's not working, and then you just rewrite it and all of a sudden it's fine.
Like, oh, hey, there it is. Yep. Yeah.
I like what you said about commenting your code too. That's a big one that I've run into as well. Because you never know when you're going to reuse that,
Right.
Or share it with somebody else that needs to use it. And then they're like, well, okay, what am I doing with this? I don't understand.
I mean, I've had even things that I wrote 2 years ago, and now that I'm going back and writing a paper about it, I have to go and rerun that code. I'm like, what was I doing?
What's the purpose? Yeah.
I'm using a lot of tools from our two collaborators at Southwest Research Institute, Rodrigo and Mark. And Rodrigo's got a lot of really cool new Python code, and most of our sort of base fundamental light curve stuff is running on this really old code from the 90s that Mark wrote. And working sort of collaboratively in a team, working with other people's code, has really driven it in how important it is to comment your own code, because these two guys are really, really good and really thorough at commenting their codes. And even with that, it can be hard to figure out, which line am I looking for? Which line do I need to change? Or where is this breaking? But if there hadn't been comments in their code, I would be unable to follow their logic.
So there you go. For any young people listening that want to get into programming, that's your takeaway from today's episode. Comment your code. That actually kind of leads into our next question. And this is, I just thought of this, and so I'll ask it. I don't know if we'll air this or not, but I think a lot of people are interested in getting into some programming, whether it be for science or something else, but they don't know where to start. And so, people like the three of us are very fortunate to have, a university that has classes and structures to kind of teach us that systematically. But for people that kind of aren't in that boat, Ryder, do you have any suggestions for how to get the ball rolling? Other than commenting your code.
Other than commenting your code, I think start simple and start slow. There are lots of great online tutorials, and just type into the search bar. Intro Python tutorial for beginners, and I think before I took my scientific programming class, that was how I started to get my foot in the door with Python. And one of the big mistakes I made was, as I followed this tutorial, I wasn't stopping sort of every step of the way to make sure I understood what I was typing. Because, the tutorial teaches you how to use while loops to make a number guessing game. And it's easy to, copy their code into your IDE and hit enter and say, cool, I coded a game. But I think as you're getting started, if you're using these sort of online, less synchronous tools, it's really, really important to take it slow and make sure you are understanding and cognizant and deliberate in every step you do, and every line of code and every command and every bit of syntax you write, to really start understanding it from the fundamental level. And know that you're not going to be making games on your first day or first week of coding. And so again, sort of being able to be patient with yourself and sort of build it from the ground up.
It's kind of like reading comprehension. Oftentimes I'll read like 2 pages of a book and I'll hear the words in my head, and then I'll stop and think, wow, I have no idea what I just read. Nothing. It's totally gone. So, all right, cool. Yes.
Experience when I was trying to teach myself Python, going through those tutorials, and I made it through all of them in like 4 hours, and I was so proud of myself. And then you go back and be like, try to actually do it for yourself. It's just like, I learned nothing. Mm-hmm. Really good at following instructions, but
I think that experience is also true on like a broader scale of learning in general. Even in class, if your professor is working through some physics problem on the board, it's really easy to be like, yeah, that makes sense. Of course you would do that. Yeah, okay, And then you go home and you try and recreate that, and you're like, wow, I have no idea how that happened. And so I think that's also important for us to do just all the time whenever we're learning, is to ask yourselves, do I really get what's going on here?
Yeah, you need to not trick yourself into thinking that you get it.
It's
easy to do that. Absolutely. Yeah.
And I'm going to segue this straight into my next question, because I think it works out really well. Doing undergraduate research. This is not a thing that everybody does. They recommend it, but not all of us get to do that. And I personally found that it was a really great way to take all of this stuff that you're learning and actually apply it to something. Did you kind of get that feeling too? Was there anything about undergraduate research that you thought was really effective or really helpful for you moving forward?
Absolutely. Yeah. I think, well, to start off in terms of coding, you do your programming and take your programming class, and you do all of the tutorials and all of the sort of like structured assignments that the professor has for you. But getting into research and being given just a task, and John said, do this thing, write a program, that a set of functions that can query the National Weather Service database and parse and output them in certain ways, and there's a lot less of a structure because it's like a real task, a real problem that you're trying to solve, rather than something that's already been done and the professor's trying to see if you know how to do it as they know how to do it. And so sort of the sort of realism and authenticity of it, and sort of in the coding, but also not in the coding, and the sort of general everything of it. The messiness of research is so different from the types of problems that you do in your formation and dynamics of planetary systems homework questions. Those are, they give you really clean values, and you type them into the calculator or do it by hand because they're all powers of tens, and you get these really clean values with perfect measurements with no uncertainties, and you get really clean answers. And one of the sort of profound things about getting involved in research on an actual project, working with actual astronomical data and trying to answer questions that don't have known answers yet, has been how untidy it is. And that's sort of, in some ways it's helped to because there's this, I'm not sure what the word I'm looking for, but there's this sort of intimidation that you get from the term research, like, oh, I want to get involved in research, and you think like, oh, I like don't know what I'm doing, I can't do like research, and I think the fact that getting involved in undergrad research and figuring out that, oh, it's just this big old mess and a whole bunch of questions that people don't have answers to, and like there are people with a lot of experience and a lot of knowledge, and there's people with not so much experience and not so much knowledge, but there's no like expert that has all the answers, sort of makes it feel a little bit softer and a little bit less intimidating. Yeah, Colin, the class that you were part of for a very brief period of time, the 3400 research methods class, that was one of the big sort of messages and takeaways that a lot of the students there sort of reported, and also something that we were trying to push was like, research is messy and there's no right answers, so if you don't have the right answers, don't feel intimidated or don't feel
right
sad because no one has the right answers, because there aren't answers yet.
Well, yeah, I think that's kind of a very different, like a totally new thing, in that, basically up until the moment you start doing research, once, up until then, you've been taught by someone who knows, definitively, even if you're in like a quantum mechanics course where not knowing is built into the physics, someone is telling you that not knowing is built in. And this is, for a lot of people, the first time that they're like, oh my gosh, no one here is telling me the thing. It's just, we just have to figure it out, And so that's kind of cool. Yeah, it's probably an important thing to learn and experience, for one's self. That is how it is, and that's okay. That's the whole point. That's what learning is on a real, very real level.
That's science. That's what we do.
Tara, that was my favorite part of our observation 1 and 2 classes, was those were real projects with real data, and it was super messy and frustrating sometimes.
It was.
That's like how it is.
Yep. And that was one of the things that struck me, especially in the first class that we took. Our group did all these observations of these nebula and took all this stuff, and then all of the experts from the department came and looked at our poster and wanted to ask us questions, and it was super intimidating at first until I realized they don't know either.
Mhm.
So I'm essentially telling them what this is all about. I know more than John Bally about this nebula. Like, that blows my mind. And I've come across the same thing in my research too. It's nuts to think that there's so much stuff that nobody knows.
Well, astronomy has always been one of those fields that kind of readily admits our ignorance. You know, we're like, man, there is so much that we have just no idea about at all. And that's what makes it so fun, is that basically anywhere you look, there's questions to answer. And so there's like limitless possibilities.
Well, that's what's
questions.
that's what's so that's what turned me on to astronomy. Was it's literally the biggest scale of science that there is. Like, there's no science that operates at a larger scale. And so yeah, the amount there is to learn, and the amount of questions, and the amount of like different kinds of work you can do in astronomy. It's such a broad field too. It's awesome.
Yeah, it absolutely is. And I think I like having this undergraduate research experience, because I think it really does prepare you to go on to at least grad school or moving on in your professional career. And you mentioned you're moving into grad school now. You're heading to Northern Arizona.
Yes.
What's
Yeah.
next for Ryder Strauss?
Oh yes. Yeah. I'm going to be moving at the end of July to Flagstaff, Arizona. I'm going to be joining the Department of Astronomy and Planetary Sciences at Northern Arizona University. I'm going to be working under Dr. David Trilling, who's a very, 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 very nice and wonderful and cool man who I'm very excited to work with. And I'm going to be continuing studying the outer solar system, continuing studying trans-Neptunian objects. I won't be doing occultations anymore. Boo-hoo. But in some ways that's sad, and in some ways that's exciting, because I think I've really sort of dug into this occultation thing, and it'll be cool to branch out a little bit and learn some different kinds of research. But it'll be more along the lines of these like large scale outer solar system surveys, sort of more structural and dynamical. It's on a project called DEEP, which stands for the DECAM Ecliptic Exploration Project. It uses the DECAM, or dark energy camera, down at, I believe, the Cerro Toldo Inter-American Observatory in Chile. It's this really, really, it's like a degree field of view camera. So these like really wide field survey images. I'm already studying those and finding TNOs and identifying and characterizing them. And it seems like a perfect fit for my interests, which are observational work with telescopes and the outer solar system. And those are the two things that I really wanted to study, and they're going to let me do both of those at the same time.
Looking back on your last 4 years, your undergrad, was your undergrad a 4-year experience?
Yes.
Okay. Yeah. Okay. So looking back on those years, was there a particular moment that seems to have been the turning point? You know, something that like before maybe what your future would look like was a little more ambiguous, but then, you know, this thing happened and then it was all clear.
I think there were two. And the first one was in some ways the biggest one, as at least as far as figuring out that CU was where I was supposed to be and astronomy was where I was supposed to be. But I did not declare as an astronomy major at CU. I was a pure physics major, and I thought I wanted to do, you know, laboratory physics. And that stuff is super cool. And as I got sort of farther into my undergraduate career, I got to sort of ingrate myself in the physics program and get to know faculty and students and sort of find my love for that. But at the beginning, I something felt like it was missing, and I wasn't super happy being at CU. Obviously, it's a challenging adjustment for everyone. You've moved out of your house with your family, and you're an adult for the first time, but like not really an adult, but you're like kind of an adult. There's like the most of an adult that you've ever been, and it's not super easy, and I wasn't super happy. And I wanted to like find I found for the next semester I wanted to find a class that I was like excited about. And I'd always had this sort of interest in astronomy. I've had the Meade telescope for many years, and I always loved to watch Through the Wormhole with Morgan Freeman, and I've got the DVD set of Carl Sagan's Cosmos, and all that stuff. And so I decided to enroll for Zach Berta Thompson's Intro to Astronomy class. And boy, oh boy, is Zach Berta Thompson the reason that I am an astronomer now. This was one of the first classes that he had taught at CU. He was a brand new professor. And it was my first astronomy class ever that I'd taken. And his passion and his energy and his enthusiasm is just the sort of infectious miasma that swirled around him and around everyone who he interacted with and talked about astronomy to, and I think that was sort of the big switch that flipped, and I said, oh my gosh, he is so excited about this, and he has gotten me so excited about this, and being excited about this feels really good and really cool and happy, and I want to continue to make sure that I feel really excited about this. And yeah, and at that point I switched my major to astronomy, and I've been an astronomy major all the way through. And then the other big turning point, I'll be a little less long-winded, but was getting the job with John. As I said, this was a little bit of a I want a job because I need some money, and it'd be cool if I could get that job in research, like in the department. And being part of this project has been such an amazing learning experience and so rewarding. And seeing that first light curve with the very clear dip in it, and the sort of buzz and high you got from that positive detection, I think that was like the bug that bit me and said, no, you want to do research, and you want to keep doing research, and that bug has not yet let go after a little over 2 years working on the project. So I'm relatively confident it's here to stay. Yeah.
Nice. That's a great story. It's always really cool to hear about, a student that is kind of like, I don't really feel like this is my thing. I'm not super stoked about any of the stuff I'm doing. And then all of a sudden it all comes down and you're like, oh yes, this is exactly it. I found it. So
it's amazing.
Okay, this last question is just kind of a fun. We always ask, our guests this kind of like funny, just a silly question. I don't know. It's not silly. It's real. Sorry, I'll stop. Down talking our podcast. Is there a particular solar system object that you get super stoked about? Like, do you have a favorite planet or a favorite object that you have confirmed the existence of through your research, or anything in that category? Is there, if someone's like, hey, you do astronomy, what's your favorite solar system thing? Are you ever like, yes, of course, here's the thing?
Whew. That's a tough question. Maybe it might be the Jupiter Trojan Lucas. Just because that object was my personal hell and heaven for several months. I essentially I led, and it's one of the targets for the Lucy mission. That's going to be flying by five targets, 6 objects in the population of Greeks and Trojans out by Jupiter. And there was an occultation prediction for Lucas to pass right over Northern California, Southern Oregon. What's in Northern California, Southern Oregon? RECON. And so this was originally as a senior thesis effort was this occultation campaign. And so I started reaching out to the teams and all the teams that are nearby and saying, hey, Sisters, Oregon, would you be willing to hop on a bus and drive 4 hours down to Southeast Oregon and observe at 1 a.m. for me? Because it was a really small. This is another example of an object that had lots of occultations before, really narrowing down the uncertainties on those predictions, and so I this was like a super targeted campaign. So I had to reach out to these teams and say, hey, if you're interested in observing, I'm going to have to ask you to, at midnight, drive to where the shadow will be, because if you observe from your house, you will be useless. And I got involved with Mark at Sweary, who had actually led a couple of previous occultations on this object, because he's one of the big occultation leads for these Lucy targets, and he said, I've got an even better prediction for you. Here, check this out. So he sent me an even better prediction, and it was many kilometers off from the previous prediction. So I had to text the team that I said, hey, you want to drive 2 hours? Well, instead, it's going to be a 5-hour drive if you're still in. And it was very slow moving for a couple of weeks. It was about 2 months, 2 or 3 months. This effort was going on, and then like the last 1 or 2 weeks, we really wanted to start figuring out how we wanted to do this deployment, and the occultation prediction was changing every couple of days, and it was these like crazy systematic offsets. And Sisters Oregon, one of our communities, got, I think, 12 high school students and 2 teachers and a bus driver, all to like make an overnight field trip out of it. And so it was like 4 days before the event, and we'd booked a hotel down in the southern part of Southern Oregon, for them to stay the night so they could go and deploy. And then I wake up the next morning and Mark has sent me a message that there's a new prediction. And the new prediction brought it way back up north, and their current plan would no longer work. So I called Prima and I said, hey, predictions changed. Would you be willing to travel elsewhere instead? And they were super good sport about it. The strategy was, I had all these teams already like on board and committed. So they like felt like they had to do whatever I wanted. But we had to cancel the old hotel reservations and book new lodging at a new hotel. And I don't think we sent the final prediction deployment plan out to them until like 4 hours before the deployment. It was we're like, yep, we know you're getting in your cars to drive there right now. This is where you need to be. It was horrible and super rewarding, because we eventually went with a super narrowly spaced deployment. We had 9 sites, 9 recon sites. We spaced them at 5 kilometers apart. So you're spanning 45 kilometers. The object itself was 30 to 40 kilometers. And so our spacing was the size of the object. We were dealing with uncertainties in the offset of the shadow path of on the order of a kilometer or 2 kilometers, like really unprecedented levels of precision for this kind of occultation. Even RECON, they had more telescopes, so they were able to spread a little bit more about the uncertainty zone. But we decided to do this really aggressive approach where if it had been offset by 40 kilometers, we would have totally missed it. We got 4 positive detections and 2 useful constraining chords. We got enough to see a non-spherical sort of bean shape on the object. And it was super rewarding and super exciting to see the data and see the reports coming in, because they were all observing and I went to bed because I had an exam the following morning. And I woke up in the morning for the exam and I look at my phone and I've got all these emails like, oh, we saw it, we saw the blink, we recorded it. So I'm like, yes.
So did you ace your exam then? Were you like riding that high through your
Yeah.
exam?
I was like the adrenaline of the high was all the way through.
There you go.
But yeah, so I think for that reason, Lucas might be a favorite object, just because the amount of effort I put into that campaign.
You are very intimately connected with that particular object, which is more so than like I can say, well, Saturn has some cool rings. So
exactly.
I guess I like Saturn. So cool.
It's not strictly the most interesting object, but
but it's the one you have a relationship with. Yeah. All right. Well, Ryder, thanks again for joining us. It's been a pleasure to have you and learn all about RECON and kind of what you're doing.
Yeah, thanks for entertaining my long-winded answers to your questions.
No, it's all right. That's why we ask them, is to kind of hear all about your thoughts. So